So I'm here to give you a slightly different perspective, I guess, on some things that you've heard about a lot this morning. And part of the reason for doing this is to show you how important it is to have a different perspective on lots of things. And so I work in a group that includes a lot of different people, ranging from mathematicians, statisticians, physicists, public health people, economists, all over the place. We don't have a library scientist or someone with a degree in divinities, though. So I'm starting to rethink this diversity business. And the kinds of stuff we do is that we make the big simulations of infectious disease. In this picture of Alabama, we're zooming in. The red places are places where there was a lot of flu in one particular run of a simulation, and the green places are places where there wasn't so much flu. And I just wanted to give you some idea of the scale and also the resolution. And I have absolutely no belief that in any particular flu outbreak, the houses that have blue dots on them are the ones that are going to get infected. That's not the way these simulations work. But when we draw many instances of these random processes and aggregate results up to the level of blocks of people, we do tend to get interesting phenomena, spatial and demographic patterns that you don't get with the big differential equation-based models. So I'm going to talk a little bit about that today. I'm going to start off with a picture that you've seen several times already today. But I'm going to think about it maybe a little bit differently. So these are states of infection, susceptible and infectious and recovered. And you could elaborate on this a lot more. There's one arrow that takes a susceptible person back into being a susceptible person, another one that gets them infected. I'm also going to talk about people. So here I've got 4 different people. And I'm going to talk about each person having a little machine in them, essentially, that's keeping track of what their disease state is. So this is the way we simulate disease spreading over a population. We have millions of people instead of just 4. And we have rather more complicated disease models than just the 3-state model. But let's think a little bit about what it is that makes this simulation a complicated thing to do, or actually what makes the spread of disease complicated. So I'll take an outbreak that's occurring in these 4 people. At time 0, one of them is infectious, the one over on the far left there. And at time 1, somebody else gets infected, and the first person recovers. And you've all seen this several times today. That doesn't look like a very complicated thing. But when you start to think about it, making a formal mathematical model of this, one way to do it, and it's a very standard approach in the physical sciences, would be to say, I'm not interested so much in exactly what happens to just one person. I'm interested in what's happening to the whole system. So on the right here, each one of those little circles represents a configuration of the whole system, like who's in state S, who's in state I, and who's in state R. And as people get sick and recover, as the system moves from one configuration to the next, it moves from one circle to the next in that big picture on the right. Now the problem with this is a very well-specified thing, and to know everything you need to know about how a disease is going to spread in those 4 people, you just need to know all the transition probabilities between each one of those circles and every other circle. The problem is that a small system, even with 4 people, has an enormous number of configurations. So if each person can be in one of 3 states, that means that 2 people can be in any of 9 configurations, 3 people can be in any of 27, and 4 can be in any of 81. So there's 81 circles, little circles in that thing on the right. And it gets much worse than that, of course, because in principle, you could go from any configuration to any other configuration, and that's, in this case, what I've got written down there, m to the 2n over 2 possibilities, where m is the number of states and n is the number of people. And that works out to 3,240 possible transitions in that thing on the right. That's for 4 people, and what we would really like to do is study a few million people. So you can see that there might be a slight problem with this approach. This is again, sort of the opposite approach that we're taking this morning. Instead of starting with the simplest model you can think of, I just start with the model that I know is absolutely complete. It's got all the information I might ever want to know in it. And I'm going to try to chip away at that model the way a sculptor chips away at everything that's not part of the sculpture until I've got the model that I can really use. So why is it? What is the real problem with having that many transition probabilities you have to figure out? In my view, pragmatically, it's that I watch a disease go through a population a couple of times. And even when I do that, I don't see all the transitions between all the configurations of the population. I only see a few of them. And if you've probably all had classes in linear algebra, so you know that for linear equations, if you have n parameters, you need to know n pieces of data related to fit those parameters. And it's very similar in other kinds of models, especially this model. I've got 3,200 things I need to find out, and I've only got 3 or 4 observations. There's absolutely no way I'll ever get an estimate for all those transition probabilities. So I have to simplify the model somehow. And I can think of 2 approaches that are widely used to simplify models. One is to make aggregates of these individual people, and I'll go through this as I go. And what happens is that you group a bunch of people together, and then you have to think statistically about what happens to them, probabilistically about what happens, and say, well, I'm going to look at, say, the mean behavior of this group of people. Another way is what's often called a generative model, where you make some sort of causal model, probably not in the same sense that Eric was using the word causal, but similar. And you can simplify a model by making some assumptions about what causes things to happen in it. And I'll describe these 2 ways of simplifying this model. So on the left, I've got my big, I didn't mention it, it's called a Markov process. All the different configurations and all the transitions between them. And on the right, I've got a little graph that graphs the number of people in this system who are susceptible versus the number who are infectious. And I can find a group of configurations in which every configuration has the same number of people who are susceptible and the same number who are infectious. So I'm going to map that whole group into one point in the right-hand picture. And I'll find another group that has, in this case, a different number of susceptible and a different number of infectious. What happens if I do it in this particular example with just 4 people is I go from 81 configurations down to 15 little dots on that diagram on the right. And I can make transition probabilities among those dots. And it doesn't look like it's all that much simpler maybe on the right, but trust me, it's significantly simpler. It doesn't scale as an exponential in n, it scales as n squared roughly. Still, for 4 people, it's 105 transitions to figure out, and you're not going to be able to do that with 1 or 2 pieces of data. So that's the approach I was calling aggregative or statistical approach. A different approach, really, is putting some causality into the model. So I know some things about allowed transitions in this model. I know you can't go directly from being susceptible to being recovered without being infectious. And generally, you can say somebody who's infectious recovers after some time with a probability. So you can say something about that probability distribution. And then I know that because I'm thinking about infectious diseases, you only go from being susceptible to being infectious if you're in contact with an infectious person. So instead of just having these people sort of mysteriously get sick, I'm going to say the reason they get sick is because this person over here infected them. What I'll need in general is a bunch of parameters saying how likely it is that if, say, person number 2 is sick, they infect person number 1, or they infect person number 3. And I was just noticing actually the other day, I don't know if this is a coincidence or what, but this also reduces the number of parameters you need from something exponential in n down to about n squared parameters. And this is the way that kind of a model looks. Instead of just having these arrows, I have I have probabilities of following each of these paths in the diagram. And I know something about what those probabilities are in terms of rather a smaller set of parameters than I was starting with in the big Markov chain picture. So in the bottom, for example, if I know that the bottom two people are both infectious, and I know that the one on the left is connected to both of the other two people, the susceptibles, that person affects their probability of becoming infectious. And likewise, if the right-hand person is only connected to one other. So they have less of an effect on the whole population. But you can just write down very simply what the rules are for combining all these things. However, as I pointed out, n squared is still too many parameters, especially if you're trying to fit with just a couple of data points. So you can make more assumptions. And here on the left, I've made an assumption that everything behaves sort of as the mean. And this is a discrete time formulation of the differential equations you've seen several times before now. I won't really talk about this. I'll just say that you can go from having to find 105 transition probabilities down to just two parameters in this case, the beta and the gamma. Similarly, if you take the causal approach I was taking, and then say all of a sudden, well, I'm not going to worry about what the individual probabilities of one person affecting each other person are. I'm just going to say they're all the same. If I did that, I would end up actually with a very similar set of equations as the ones that you get through the other route. It's not terribly surprising because you've done similar things to your model along both routes. The problem is that none of these assumptions really are very nice things to make. So essentially, they boil down to saying that everybody in the system is the same. It's a homogeneous system. That their behavior doesn't, that you can say exactly what they're going to do. Their behavior isn't really affected by things that they know or things that they want to do. And finally, because of these products that show up, like S times I times beta, you have to start talking about fractional people, which is kind of confusing to most people in epidemiology. So what I want to know is, somewhere, I've got these models that are too complicated to ever fit to data, and I've got these simple models that don't seem to represent what's going on all that well. How can I somehow bridge that gap and end up with a model that's simple enough that I can work with it, and yet maintains enough of the representation that I need to get reasonable results out of it? And I think the way to do that is to bring in both biology and sociology, maybe anthropology, I'm not sure exactly what it is I'm asking for, to decompose the problem and to let more people than just the MDs or the infectious disease people look at the problem. So on the left, I've got between the two people represented as circles there, some probability for transmission. The red probability is high and the green probability is low. And to me, that's something that comes really from the biology of the problem. How likely is it that somebody is going to be sneezing or that somebody has gotten sick in the first place? Whereas in the middle, there's a network of people. All you can really see are the edges connecting these people in concentric circles. And biology is really not going to tell me very much about what that network looks like. And it's that network that the disease sees when it propagates from one person to another. It doesn't know where it's going. It just knows that this person's in contact with those, and those are the people that this pathogen can get to. And it's only when you put them together that you really get an epidemiological model that's useful enough to say specific things about specific outbreaks in particular populations. OK, now I'm going to shift gears a little bit and give you another perspective on something that you've heard about again this morning. It's always a challenge to give a talk like this with people who work in the same field with you after several of them have gone, because you have to think of some new way to say what they've said before. There's not that many things to say, really. So I'm going to talk about, for a few minutes, about just a graph. Each of these dots, we can think of them as representing people, or they could just be a graph. And I'm going to throw edges down at random in this graph. There's a randomly chosen edge. And I'm going to keep doing it for a while. And I'm going to keep track of which edges are all connected by a path. So the green edges, the green dots are all, the green edges show things that are all connected in one path. The purple one is a different path. And I'm just going to illustrate something that I've known about for a long time, but it's really hard to appreciate how dramatic this effect is. So what I'm going to do is add these random edges to a graph of, well, for this particular plot, I did, I think, 100 dots. There's 20 in that picture I was showing you. And I want to know, how likely is it that every single node is connected to every other one along some path as I add more and more of these random edges? And I can tell you that if you've got n points and you only have n minus 2 edges, you can't possibly connect them all together. So I know that the point in the lower left has to be there. And I know that if you have that many edges at the upper right, you have to have a path between every single node in the graph. I'll leave that for the reader, as they say. And the question I have is, what's it look like somewhere in between? And one reasonable hypothesis might be, well, it's sort of smooth. It goes from one to the other, and that's what you might expect. That would be a linear thing. All right? So I'm going to do this for 20 dots. And you can see that it's a random thing. So I'm doing it once on the left and separately on the right. And they're not progressing at exactly the same speed. And in fact, the one on the right is now completely connected. The one on the left isn't connected yet. It doesn't get connected for another 6 or 7 dots. So what does this look like? If it took me 38 steps to get to this point for these two graphs, or 31 for one graph and 38 for the other. If I did that over and over again, how often would I find a graph that's connected as a function of how many edges I've thrown? Well, this is what that looks like. It's really fast. Once you get past this threshold, which we know about, there's a critical point at which all of a sudden the graphs are almost always connected. This is called a phase transition. And remarkably, this is very, very closely related to the phase transition of boiling water, or making gelatin, or turning a lump of iron into a magnet. Same kind of behavior in all those systems. And in fact, I think a lot of the study of phase transitions was promoted by people who realized that what they were seeing in epidemiology was a phase transition. So I've made it this far through the talk, and I haven't mentioned one particular word, and I'm going to have to mention it right now. This is R naught, by the way. R naught is this critical parameter right here. And the reason I wanted to show you this particular view of the phase transition is that it's not simply that as you vaccinate more people and reduce R naught, you're getting this nice, smooth decrease in the number infected. This is really the herd immunity effect. That you don't have all that much effect until all of a sudden you hit this threshold and bam, hardly anybody's getting infected. So it's really important to know where this threshold is, and also a little bit about how fast the phase transition occurs. All right, so that's about random graphs. That's a sort of mathematical or physicist approach to phase transitions. And I want to talk a little bit now about the importance of network structure. So social networks are not exactly random. There's structure in them. And I want to know, how much does that structure affect the way things happen on social networks? So I'm going to take two examples of different social networks. One is and they're changed by the way the disease spreads through the population. So in one example, I'm going to imagine flu spreading, and when someone in your household gets sick, there's a little household in both the left and the right. The 2 green dots are supposed to be like adults, and the 3 blue dots are like kids. On the left-hand side, when somebody gets sick, nothing changes in the household. Everybody still mixes with everybody else. On the right-hand side, if somebody gets sick, one person in the household is taking care of that sick person. And if somebody else gets sick, the same person takes care of the other sick person. Now, you can imagine in many households who that one person who's taking care of everybody might be, but I won't comment on that. Obviously, on the right, there's less opportunity for the blue and the green dot, the far left, to come into contact with the sick people. I'm not saying that you can actually isolate people this way. I'm just saying, what would happen if you could? Well, we did some simulations in some very specific populations. We looked at Seattle and Miami because the demographics of households there are very, very different. On this particular plot, you can't see the difference between Miami and Seattle. What you can see is the difference between the top curve, where everybody was mixing in households, and the bottom curve, where there was a single caregiver. And what the curves are is I'm changing the transmissibility. So as the person-to-person transmissibility of the disease goes up, the average attack rate, which means that the average over a lot of simulations of the number of people in the whole population who get sick, is significantly different by making this change. So you might go to the policymakers and say, we've got it. All you have to do is convince everybody to take care of their households this way. But that's not quite right. And why is it? Well, here's what the effect of changing the caregiving strategy is. But think about the situation that you have to work with and the data that you have to work with. What you might have, if you're really lucky, is some idea, of what the attack rate is. So you just have a point on that left axis that says, this is what the attack rate is. And you've got 2 models. One model is where everybody's taking care of mixing in the house, and one model is where there's a single caregiver. And I can fit either one of those models just fine to any of those attack rates. So now think of these 2 models in your head, all calibrated, modeling all the data you've seen so far just fine. And now say, what happens if you suddenly have a massive advertising campaign, you bring in your super PACs, and they're instead of electing a president, they're going to prevent a flu outbreak. So they're telling everybody, this is the way you need to take care of people in your household. Well, it could have a very big effect, or maybe not. As I think it's the Mock Turtle says, either everybody cries when they hear this poem, or they don't. And we don't know which situation we're in unless we know what the network looks like. So is that such a problem? Are there really all that many networks to choose from? Well, for 5 people, there's 21 different networks you can draw that are really distinctively different. For 14 people, I don't know how to read that number, quadrillions, quintillions, or something. There's a lot, and it grows really fast, much higher than exponential. So I'd like to know, what do I need to know about the network? I'm obviously never going to measure the social network, which is, of course, always changing, and figure out which exact one of those 29 whatever networks it is. What do I need to know about it? Well, I should know that not all random networks are the same. And that's what I was trying to say about the structure in the graph. So the structure that I had been talking about was just in households. Changing the structure just a little bit in households has a big effect on things. So I want to say something about what the space of possible social networks looks like. And I have to do that by embedding it in the space of all possible networks. So this gray blob is meant to represent all the possible networks. If you were doing a study that said, I'm going to choose a network at random from all the possible networks, you would get any one of the graphs that's in that space with the same probability as any other graph. That doesn't necessarily mean that you get any one of the social networks with the same probability as any other graph. Because you can find little regions in this space where networks have some particular property. So I've drawn two regions here. One is called scale-free graphs, and one is called small world graphs. You may have heard of these. There are a lot of popular books about networks, and social networks in particular, that talk about these. And you can actually prove things about these kinds of graphs, random graphs. You can prove things like there's no epidemic transition in this particular kind of a graph. But that still doesn't tell us where the social networks are. And no one, to my knowledge, has any idea how big the set of things that look like possible social networks is and where it sits in this graph, especially relative to any other class of networks that we know about. And I'm not going to answer the question here because I don't know the answer either. That's something that you guys need to figure out, right? One thing we have done, though, and I'll skip this. I'll go through this really fast, but it's not too confusing. Is to take any graph that we're given, and we can always generate one that's a little bit more random by shuffling some edges in the graph. That's all I'll say about that. And when we do that, we're sort of walking around in this space at random, like a random walker going somewhere. If we start with one of our social networks, it turns out to sort of diffuse into very random kinds of graphs very quickly. Whereas if we start with a random graph, there's almost no chance that we will hit a social network. It turns out that social networks don't seem to be a very big part of this space. And why does all of this matter? Here's what happens if we run epidemics on these graphs where we start with something that we think represents a real social network and start shuffling edges and see how the epidemic curve, the number of people infected on a given day in the top left, changes. And it changes pretty dramatically, and there's biases in how it changes and stuff like that that are very interesting. But what really, really scares me is the picture on the bottom right. Because we take each of these networks and we do some sort of intervention against the spread of disease. School closures, vaccinations, what it says there, work closures, social distancing. And on the left is what happens to those four interventions in the original network. And it turns out that school closure is the best thing you can do in that network, and social distancing is the worst. And on the right is what happens when we've randomized that network a lot. It turns out that in the random network, school closure is the worst thing you could do. And they're almost inverted. So it would be very nice to know whether the random network is capturing things better than the realistic social network or not. And what are the features that make the thing that make this what we think is a realistic social network be realistic? Okay. I'm sorry that was kind of fast, but I'm going to give you a summary. I'm sure you realize by now that it's traditional at the end of a talk to give a summary and conclusions and future directions, and usually you give 3 points, but I don't really expect you to remember many of the points that I've made in this talk years from now. But I'm kind of hoping that you'll remember some of these summary points. So the first one is, and Gary sort of pointed this out earlier this morning, that mathematics is really a wonderful way to talk about things that happen in the natural world. And whether or not you get thoroughly involved in mathematics or modeling, you should at least learn to appreciate that it's possible to model an enormous number of things using math in ways that really help you understand what's going on. Another thing that makes me wake up and go to work is it's possible you can get to the forefront of knowledge. So right in this half-hour talk, I've told you about a problem that is probably basically understandable, a problem that nobody knows the solution to. And it's not necessarily because there's no solution, it's just because we haven't had enough people looking at it yet. And because of the way science works, these things, you can know more about math than Isaac Newton knew. You can know more about physics than Albert Einstein knew. Because everything builds on everything else, and they didn't have available the kinds of accumulated knowledge that you have. If you do graduate study, what my advisor told me, which is very true, is that you pretty much have to focus in on a topic to get your dissertation done. Otherwise, it'll never get done. And by the time you get to the end of that dissertation, you know more about that topic than anybody else in the world. It's true. And then you go on from there, and the people you work with have all been through that process. So you're working and talking on a daily basis with people who know more than anybody else in the world about something. I just think that's amazing. And finally, you've got to believe that you can make a difference in things. So I've done modeled a lot of different things over the years. I've modeled quark gluon plasma. I've modeled foreign exchange prices. I've modeled the carbon cycle in Biosphere 2, natural language processing, all these things. And I kind of spent a couple years on each of them. I've worked in epidemiology for 10 years now because it's the one that I've hit on that really seems to make a difference. I think that things I can do can relieve suffering in the world. And that's what makes me happy. So that's why I got stuck on epidemiology. So I hope that you all become epidemiological modelers and help us out and figure out the answers to the questions that we can't get. But if not, I hope you at least take this into account in whatever path your career takes you on. Okay.
Kelly, Virginia Tech. You talked about how it'd be nice to know whether we had a random or a social network that we could count on in order to make certain decisions, policy-making decisions. Would a kind of public campaign about trying to, establish a social network help in terms of, like there are campaigns about washing your hands and certain things that you should do at certain times of the year, but a campaign to help establish social networks, at least within the family, always have one person taking care of the sick or something like that. Would that help? Would that be feasible?
Okay, now you've caught me because I can't tell what's feasible or not. I think some public health messages do get out. People's hand hygiene goes up, especially in times of big outbreaks. What I'm trying to say, though, is that until I have a model that I think is fairly realistic, I don't really know what the best things to concentrate on. How do you prioritize all the different possible things you could do? So I'm hesitant to say, for example, that you should go out and have a public health campaign that says have a single caregiver and isolate sick people. It seems like a very reasonable thing to do. But as I think Sarah was mentioning, if you've got a finite pool of money to do stuff with, you need to prioritize. And I'm just hoping that I can make more defensible statements about what are the priorities in this case.
Hi, I just had a question. When you talked about changing the structures in households, were you talking like the networks in your household and whatnot? Can you give an example of changing the structure in a household? Like if somebody has an infection, like the members of the household wearing masks, or is that what you're talking about, changing the structure?
Yeah, there's lots of ways to change the way the network is. So those edges in the network slide I drew, they represent contacts across which it's possible to transmit disease. And maybe you can make a physical barrier like a mask that would remove that contact. Or maybe you could vaccinate someone or give them drug treatments prophylactically. But the easiest thing to do, and the thing you can always do when, even if therapeutics aren't available, pharmaceuticals aren't available, is to just physically change your contacts with someone. Don't go into their room unless you need to go into their room. And it has other effects. If you close a workplace or a school, there's lots of repercussions. If you have 20 people living in 2 rooms, you're not obviously going to be able to do much about the way they mix. But if you have a place where you can isolate a sick patient the way a hospital would, you should try to do that. The reason this came up was that CDC has absolutely nothing to do with this. They will disavow all knowledge of my work. But somebody from CDC was asking the question in the last flu pandemic. When demand exceeds capacity at a hospital, there are going to be a lot of sick people out there who won't be in the hospital. Now, usually CDC doesn't offer advice about taking care of people at home when they're sick. But maybe in this case, there's some advice they could give people about how to take care of sick people at home. And we were just looking to see whether it would make much difference.